Good morning, dear students. My name is Ferhan Mazher, and today is 11th May 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. This is Cambridge O levels of physics, and today we have set our hearts to solve paper 4, and we also call it alternative to practical ATP paper. And today we have selected October-November 2012 4-2 paper. This paper 4 belongs from the zone 2 or the variant 2. So let's start this paper. The time allowed for this paper is 1 hour. So let's start, and here comes the question paper in front of you. October-November 2012 4-2 paper. The first question coming up on your screen: a student investigates the speed of the water waves. A rectangular plastic tray has a layer of water in the bottom as shown in the figure 1.1. So you can see this tray, look at the edges of this tray, they are little leaning outward. The level of the water in the tray is quite low. So one end of the tray is lifted gently a small distance as shown in the figure 1.2. When the water is still, the tray is lowered quickly. This causes a wave to travel across the surface of the water as shown in the figure 1.2b. So what they did, they lifted this tray upward and then they moved it back very quickly. So after the water came steady, they did this. So a wave was created. The wave is reflected by the ends of the tray and travels backwards and forwards several times. The student estimates the time for the wave to travel one length of the tray to be about 1 second. Suggests a reason why the student decides to measure the time for the wave to travel 5 lengths of the tray. You see, whenever you uh, for wave to travel from this end to that end, a single length of the tray, it took 1 second only. So 1 second is quite small time, and when you are using a stopwatch to time it, because the human reaction time is also like let's say 0.3 second or 0.5 second. So the human reaction time is quite large as compare a large part of this time, 1 second. So it's not a sensible thing to do to measure directly the time for the travel one length of the tray. The wave took time to complete the one length of the tray. It will be better if you time 5 lengths of the tray, because then the time required will be large and the human reaction time will be small part of that. So the effect of the human reaction time on that measurement will become very small. So that's the reason why the student decides, okay, so I was just explaining. So let me show you the answer. Timing 5 lengths of the tray will have less effect of the human reaction time. From this, more accurate time for one length of the tray will be obtained. So when you will average it, and from there you will find the time for the one length of the tray that the wave took to complete the one length of the tray. That will be more accurate because the effect of the human reaction time on that time has decreased, because you have not directly measure the time for the one length of the tray, you have measured the time for the 5 lengths, and then you have divided with the 5 and got the time for the one length of the tray. I hope you understand. It's a bit okay. So let me show you the marking scheme. What the marking scheme says: the time for one length is small, reaction error large, compared with the time gives average. So when you do 5 lengths, it gives you the average. So the result will be more accurate. Okay, so the next part coming up on your screen is, he says the ends of the tray slope outwards. Explain why this makes it difficult to measure accurately the distance traveled by the wave. So as you go inside the tray, the distance between the edges of the tray is decreasing. The edges of the tray, they are bending outward. So it is quite difficult for the scale because the distance between the edges is decreasing as you move into the tray. So it's become difficult for a meter rule to go into the tray. Level of the water, and the level of the water is lower in the tray. So scale will not be able to reach the water. Level of the water is lower in the tray and the scale cannot reach the water. As you go into the tray, the distance between the edges is decreasing because they are bending outward. So let me show you what I am talking about. You see these edges, they are bending outward. So here at the top, the distance between the edges is larger, but as you go down, the distance between the edges is decreasing. So for a scale, if some scale fits on the top, it will be difficult for the scale to fit here at the level of the water. So I can measure that length of the water also, but it becomes little difficult, you can say. So that is my answer. So let's have a look at the marking scheme. That the answer is not that easy. Distance traveled by the wavelength of the tray varies, cannot place rule close to the water. Okay. If the edges were straight, vertical, then it was very easy. If the edges were vertical. Okay. Describe a possible method of measuring the distance traveled by the wave. You may use a diagram in your answer. So let me show you. I have improvised my own. So here you can see I have used a scale, and that scale is little higher than the tray. And then I have used the set squares. And by using the set squares in this way, I will be able to bring this point of the water when it touches the edge. And from here I can check what is the reading here, and by using the set square like this on this, I can check what is the reading here, and then I can find what is the distance between this point A and this point B. Use the set square and the horizontal scale as shown in the above figure. Okay, so that's my answer. So let's have a look at the marking scheme. Clear and sensible description. For example, ruler viewed from vertically above perpendicularly, use the tape measure flexible, or use my answer may be on the diagram. For example, ruler and the eye above, ruler and the set squares. We have given this answer. Okay. So let's move to the next part. He says, here he says the student measures the depth D of the water. He has two identical 30 centimeter rulers. Part of one ruler is shown in the figure 1.3. Explain why it is difficult to measure D using only one of these rulers. So if you want to measure the depth, you cannot use this ruler. Will cause a little problem because at this end you can see this space. The zero, the graduation, the calibration is starting from here. But here you have some space which has no graduation. We call it dead space. So there is a dead space at the end of the ruler. It will cause zero error. So whenever you will measure the depth of the water with this rule, the reading will be always less than the accurate depth. So we call it, this is the negative zero error, because it will always give you less value as compared to the accurate value. Then let me show you the marking scheme, what the marking scheme says. Zero error, dead space at the end of the ruler, or zero or on ruler not at the end. Zero on the ruler is not at the end, base of the tray. Okay, so then they ask us, describe a method of measuring the D using the two rulers. You may use a diagram in your space. So by the use of another ruler, check how much is the length of this dead space. and then use this ruler to find the depth, and then whatever will be the reading, add the length of this dead space in your measurement, and so the correction will be done and you will get the correct value. So let me show you. So you can see this is that ruler which I want to use for the measurement of the depth, and this has a dead space at this end. So with the use of another ruler, I will find what is the length of this dead space, and then with the help of this ruler, I will find the depth, and in that depth measurement, I will add the length of this dead space, and then I will get the accurate depth. By using the two scale, the length of the dead space can be measured, add the length of the dead space into the depth to get accurate value of the depth. I hope you understand. Let's have a look at the marking scheme. Use the second ruler to measure the length of the dead space, length of the dead space added to the ruler. So you get the reading of the depth. Okay. The student repeats the experiment for different values of the depth and calculates the speed v of the wave for each value of the depth. Figure 1.4 shows the student's results. So here we have the depth of the water and here is the speed of the wave. On the figure 1.5, plot the graph of the v in the centimeter per second on the y-axis against the d in centimeters on the x-axis. Start your graph at v equals to 20 centimeter per second and d equals to 0. Draw a smooth curve of the best fit. So here is that figure. Let me reduce the size so you can see the question together. So this y-axis starting from 20 and x-axis starting from 0. On the y-axis, we have to represent the velocity, speed, and on the x-axis, we have to represent the depth of the water. The depth of the water is going from 0.5 to 3, and this is going from 20 to 50.5. Okay. So let me show you. So this is that x-axis, y-axis. So first of all, let me show you. On this axis, I will write d in the centimeter, and on the y-axis, I will write v in the centimeter per second. Here 0.5, 1, 1.5, 2, 2.5, 3, and 3.5. It starts from 20, so 25, 30, 35, 40, 45, 50, 55. Then I will plot these points. Let me show you. 0.5, 20.6. So the dot will be here. At 1, 28.5. 28.5 will be here. At 1.5, 35.5. It will be here. At 2, 42.0. 42.0. And at 2.5, 46.3. So the dot will be here. At 3, 50.5. Put a dot here. Then I will join them with the smooth curve. Okay, I've tried to draw a smooth curve. Hopefully you can see this. Okay, once you are done with this, then their question is, let me show you the marking scheme. This is the marking scheme for that part. Okay, then their question is, suggest a possible reason why the student cannot take reading for the D greater than 30 centimeter. Sorry, 3 centimeter. If you look at your the speed is gradually decreasing. Oh, sorry. When the depth is increasing, the speed is increasing. Okay. So the speed will become larger and larger. So if the speed becomes larger, it will be, if the wave will travel at a higher speed, if the wave travels at a higher speed, then it becomes difficult to time it and to control that water. If the wave is traveling very fast, it will go out of the tray. It will spill out. Wave will travel very fast. As you see, the D increases, the speed increases. So if the D increases more than 3 centimeter, the speed will become quite large, quite fast. So the water will be moving very fast, the wave will be moving very fast, it will come out of the tray. The wave will travel very fast and the water can spill out. Let me check. Tray not deep enough, the water spills out when the wave made time too small, wave travels too fast. Okay. um, Using your graph suggests how the speed varies with the depth for very large values of the D. So if you look at the graph, you see the slope. Here the slope is larger, but here the slope is decreasing. So as the D will increase, the slope will continue to decrease. So at very large values of the D, the increase in the speed will be high, but the increase in the speed will be less for every centimeter increase in the depth. So let me show you my answer. Gradient of the graph is decreasing, so at very large values of the D, the increase in the speed will become very small because the gradient is gradually decreasing. So change in the speed will become less and less at higher values of the D. I hope you understand this answer. Speed becomes constant, does not vary with the D. Increase in the speed becomes smaller with increasing D. Gradient decreases with the increasing D. Hopefully you understand. So that was the question number 1. So we are done with this. A student uses an electric kettle to measure the specific heat capacity of the water. The figure 2.1 shows a kettle containing 1 kg of water. So here we have the electric kettle, here we have water in it, here we have the hot metal plate, heating element it has. Here we have a thermometer and it's an electric kettle. The kettle has a label on the base as shown. If the power of the electric kettle is 2755, it will be using 230 volt, and if the electric power is 3000 watt, then the volt will be 240 volt. If 2755 watts are used, then 230 volt. If 3000 watts are used, then 240 volt. The initial temperature of the water is 19 degrees centigrade. The kettle is switched on for 1 minute and the final temperature of the water is 53. So, you know how much is the change in temperature? The water is 1 kg. It said somewhere here. The mass of the water is 1 kg. The change in the temperature is 53 minus 19. And I think that will be something like 34. And the time for this change in temperature is 1 minute. In seconds, it will be 60 seconds. He says the relationship power multiplied time, which is heat or energy, equals to mass multiplied specific heat capacity multiplied temperature change, is used to find the specific heat capacity of the water. Use the relationship and give data to find the smallest possible value for the specific heat capacity C of the water. Give your answer to the suitable units. So I will use the lower power, lower voltage, and time will be 60 seconds. The mass will be 1 kg. Specific heat capacity is question. The change in the temperature will be 53 minus 19. That will be 34 degrees. So from there, I can find the specific heat capacity. It's a 3 marks question. Let me show you. So 60 multiplied 2755 equals to 1 multiply C multiply 34. So the C value will be 60 multiply 2755 divided by 34. And that will be 4861.8 joules per kg per degree centigrade. So that is our answer. So let's have a look at the marking scheme. 4860 when you round it off. I have not rounded it off. 4860 will be your final answer. Explain why the water should be stirred before reading the thermometer. We always stir the hot water before taking the reading on the thermometer, we want the heat to be distributed uniformly throughout the water, and we want the temperature of the water to be uniform throughout the body of the water. That's why we stir it. Heat is so that the heat is distributed uniformly in the water, and all the water has the uniform temperature. That's my answer. Uniform temperature or heat distribution. That is what we want to say. Explain why the thermometer should not touch the metal plate when measuring the temperature of the water. If the bulb of the thermometer will be touching the hot metal plate, it will start recording the temperature of the hot metal instead of noting down the temperature of the hot water. The hot metal plate will be at a higher temperature as compared to the water. Metal plate is hotter than water, so if thermometer touch it, it will record its temperature rather than water's temperature. So it will start recording the temperature of the metal plate instead of recording the temperature of the water. So that's my answer. इसके base of the kettle is hotter than the water. Okay. So next question. The student's answer for the C is larger than the accepted value. Suggests a reason why this answer is so. You see, in our calculation, when we calculated the C value, we have supposed that all the heat which is produced by the heater is used to raise the temperature of the water. We have supposed that. But in reality, this will not happen. In reality, the heat which you have provided by the heater, that will not all go to the water to raise the temperature of the water. Some of your heat is directly going into the atmosphere in the form of thermal energy. So, and plus when you are heating the water, the rate of evaporation will also become faster. So when the water evaporation will take place, the heat loss is actually taking place. So actually, we suppose that all the heat which the heater produce has gone into raising the temperature of the water. But in reality, this will not happen. There are heat losses. So our answer is larger for the C, but the real answer will be smaller. Some heat provided by the heater is lost to the surroundings. Some heat is lost due to evaporation of the water. But we have not thought that. We said that all the heat which is produced by the heater is going to raise the temperature of the water. That's why our answer of the C is little larger than the real value. Let's have a look at this. Heat loses to the kettle surroundings to evaporate the water. Power too large, time too large, mass too small, temperature difference too small. Okay, we gave this answer. Okay, so we are going to the next question. Here we have, a student investigates the behavior of a pendulum. Figure 3.1 shows the pendulum hanging from a fixed support. Okay, so here this is a fixed support, and here is the thread, and here we have a bob, and its mass is m. So it can vibrate like this. The mass of the pendulum bob is m. The student measures the time t, small t, for the 10 complete swings of the pendulum for different values of the m. She starts with the m equals to 20 gram and increases the m in 20 gram steps up to 100 gram. So first she put a bob of 20 gram, then 40 gram, then 60 gram, then 80 gram, then 100 gram. And she noted down what is the time period, time taken for 10 complete swings. So she got 16.32, 16.28, 16.38, 16.44, 16.35. So you see, the time period is not changing. It's little bit, so it reduced, here increased, again increased, and then again reduced. So in the space below, draw a table of the results for this experiment. So if you want to note down these observations, so we can make a table here, and I will make 2 columns, and in one column I will write the mass of the bob in grams and the time for 10 swings, and that is represented with a small t and is measured in seconds. So you can see I have noted them here. So this is the table which they were asking. It's a 3 marks question. Okay, then let me show you the marking scheme. Okay. Then the next question. Okay, we are done with the table. Okay, he says using the results from the table, comment on whether the M affects the T, the M do not affect the T. You see, if you look at the values, first the T a little bit increased and then it started decreasing. Mass of the pendulum has no effect on the T. For example, you can see at 20 gram mass, the time is for 10 swings is 16.32. When the 100 gram mass, the time is 16.35. So there is basically no effect. It has not changed. So let's have a look at the marking scheme. No, with experimenter, reading very close, no pattern. Okay, the readings are very close. Suggest further readings the students can take so that a more reliable comment can be made. So we were increasing the mass 20 gram. You can take a larger mass. For example, take 150 gram and or take 200 gram the mass of the bob, and then find the time. And you will observe that there will be no change in the time period. Another thing which you can do, you can change the length of the pendulum, and you will observe the time period will change. But by changing the mass, there will be no change in the time period. Take more higher values of the mass and note the time for 10 swings. You will observe there is no change. So from here, a more reliable comment could be made that actually there is the mass of the bob do not affect the time period of the pendulum. Okay, so what's the next question? Okay, then the question is over. So here we go. Okay, so I have given this answer. Okay. He says you can do this experiment again and again and take the average and you will observe the same thing. A student investigates the deviation of a ray of light by a prism. A ray of red light passes through the prism. The student places the pin 1 and pin 2 on the incident ray and the pin 3 and the pin 4 on the emergent ray. Figure 4.1 on the page 1 shows the positions of the pins and the prism. Okay, so they are talking about this. Let me reduce the size so you can see. So basically they are talking about this. There's a prism, pin 1, pin 2, pin 4, pin 3. Okay. So what they want? They want, first of all, on the figure 4.1, draw a straight line through the P1 and P2. Continue this line through the prism. Okay. On the figure 4.1, draw a straight line through the P3 and P4. Continue this line to cross the line drawn in the first part. Then he says, measure the smaller angle between the line drawn in the first part and the line drawn in the second part. Okay, so let me show you how this is done, what they're talking about. So basically they said, this is what they said. They said, join the pin 1 and pin 2 and continue this line. Join the pin 3 and the pin 4, continue this line until it crosses this line. Then he says, measure the angle between these two lines, the smaller angle. This is the smaller angle between these two lines. And that angle I have measured. Put a D here, put the cross of the D, put the cross of the D here, put the 0 of the D here, and then check what is the angle between these two lines. And that will be 35. So that's why I put here a 35 degrees. Okay. Then he says on the figure 4.1, draw a line to represent the actual path of the ray through the prism. And then the question is, suggest Why the student uses the red light? Okay. Let's first of all do that. Here, how you draw. You see, this is the emergent ray, this is the incident ray. So join this point and this point with each other, this black line, that is actual path of the light in the prism. So this is the point of incidence and this is the point of emergence. Just join them with each other. So this shows the path of the ray of the light inside the prism. So this black line. I hope you understand. So now it's more visible. Okay. Okay, then the question is suggest why the student uses red light and not the white light in this experiment. You see, we cannot use the white light here because when the white light will pass through the prism, the white light will make a spectrum on the other side. So we used a single wavelength and frequency light, means red light they used, because the red light will not make a spectrum when it will pass through the prism. So let me show you. White light after passing through the prism will form the spectrum. That's my answer. Okay. Let's have a look at the marking scheme. So our answer is right. I gave 35 degrees answer. So now we are on the C part of this question. Their question is, we are done with this. Okay, this question. He says in a different experiment, the student is asked to draw the normal at the point where an incident ray strikes a prism. The student draws a line as shown in the figure 4.2. Explain why the student's line is not the normal. Normal is a line which will make 90-degree angle with the surface of the prism at the point of incidence. So, and this is not making 90-degree angle with the surface of the prism. Let me show you my answer. So here I have shown a normal. It is not making 90-degree angle with the surface of the prism. The line drawn by the student is not making 90-degree angle with the surface of the prism. So it's not a normal. Then on the figure, draw the correct normal and measure the angle of incidence. This is the correct normal which makes 90-degree angle with the surface of the prism. And the angle of incidence will be the angle between the incident ray and the normal. And with the help of this protector, measure how much is this angle. And I have measured it and it is 32 degrees. I measured it and it's 32 degrees. So my answer is 32 degrees. 32 plus minus 2. So our answer is right. So my dear students, we are done with the October-November 2012 4-1 paper. I have tried my best to explain the concepts of this paper. And if I have made a mistake during this, I was using the marking scheme as well. Please forgive me. I'm just trying to help some students around the world. So if you find this video interesting and informative and useful, do share the link of this video onto your Facebook, onto your Instagram, and onto your Twitter accounts. Also share the link of this video with your junior students. Also like this video and also subscribe my channel. So it's a great blessing for me to be able to helpful to some people around the world. Thank you very much, sir. Have a good day. God bless you.